Hello. Today we're going to go over the group test you guys did in class. Go over all the problems so you guys understand the answers that you should have gotten, and hopefully understand it so you'll be ready for the test on Tuesday. Okay, so this first question asks about how many atoms are in 1 centimeter cubed, considering gold has a density of 19.32 grams per centimeter cubed and a unit cell length of 4.08 angstroms. Okay, so first we want to look at how many atoms are in 1 centimeter cubed. So we notice this also has centimeters cubed in it, right? So this gives a mass per volume. With a mass per volume, we can use this volume to figure out how much mass is there, and then use our molar mass of gold to figure out how many atoms are there. Okay, so we're going to take our 19.32 grams per centimeter cubed, multiply it by that volume of 1 centimeter cubed, giving us 19.32 grams of gold. Okay, then from here we can convert into moles of gold using our molar mass. Okay, that'll cancel out our grams, leave us with moles. Okay, that'll give us 0.0981 moles of gold. And then using Avogadro's number, we can go from moles of gold into atoms of gold. So 6.022 times 10 to the 23rd atoms of gold per mole. We get a total of 5.91 times 10 to the 22nd atoms of gold. Okay. Next, we want to know how many unit cells are in 1 centimeter cubed. So this again is a volume. So if we take the idea that we have our edge length here, we have a cubic cell that we can take this edge length, cube it to get the volume of 1 unit cell, and then we can use this volume to figure out how many unit cells are in that volume. So first we need to take our angstrom value and convert it into centimeters cubed. Or convert it into centimeters really, and then cube it. So 1 angstrom is equal to 1 times 10 to the 8 centimeters, so we can go from angstroms into centimeters. And this is our edge length in centimeters. And since it is a cube, we can cube our edge length to get our volume of our unit cell of 6.79 times 10 to the negative 23rd centimeters cubed per unit cell. Okay, and now we can take that volume of gold, divide it by our volume of a unit cell to figure out how many unit cells we have. So we take our 1 centimeter cubed, divide it by 6.79 times 10 to the negative 23 centimeters cubed per unit cell. And when we do that, we get 1.47 times 10 to the 22nd unit cells. Okay. Now, we want to know how many atoms there are per unit cell. So if we divide number of atoms by number of unit cells, we can get atoms per unit cell. So we take our 5.91 times 10 to the 22nd atoms, divide it by our 1.47 times 10 to the 22nd unit cells. And when we divide that out, we get approximately 4 atoms of gold per unit cell. Okay. Hopefully you know that 4 atoms of gold per unit cell is a face-centered cubic. Moving on, here we're looking at potassium. This is a pure substance. It has a vapor pressure of 400 torr when we're at 708 degrees Celsius, and a vapor pressure of 10 torr when we're at 443 degrees Celsius. We want to know what its heat of vaporization is using this information. So, we're talking heat of vaporization of a pure substance. We are talking about our Classius Clapeyron. Okay. So, oh, excuse me. We're going to use ln P1 over P2 is equal to negative delta H vap divided by R, 1 over T1 minus 1 over T2. So remember, we need our temperatures in Kelvin. Our pressures, it doesn't matter. As long as we keep our pressures in the same unit, we can keep them both in torrs. And our R value is 8.314 joules per mole Kelvin. So this 443, if we add 273 to that, gives us 716 Kelvin. This 708, add 273 to it, we get 981 Kelvin. So we're just going to plug all that in. So ln P1, 400 torr, P2, 10 torr, equals negative delta H vap divided by R, 8.314 joules over moles times by Kelvin. And then 1 over T1, 981, minus 1 over 716. Okay. If we were to multiply and divide out everything on our left side, we get 3.69. And then if we multiply and divide everything besides the delta H vap, we get negative 0.1000454. Okay. And then if we solve for delta H vap, we get 81,315 joules per mole. Or you can put it into kilojoules, which I prefer, 81.3 kilojoules per mole with 3 sig figs. There. Okay. We can then use that delta H vap and solve for a vapor pressure at a different temperature. So we have ln, I'm just going to use my original P1 here again, so 400 torr. And we solve for P2, so what vapor pressure at this particular T2, which would be equal to 373 Kelvin. Okay, so that would be equal to negative 81,315 joules per mole, making sure that our HVAP is in joules per mole, because our R value, 8.314, is also in joules per mole Kelvin. Okay, then we multiply that by our T1. I kept my P1 the same, I'll keep my T1 the same, and then my T2 is at 373. Okay. If I multiply everything out on the right side, I get my ln 400 torr over P2 being equal to 16.3. If I take both sides to the E, that will get rid of my ln value. So I'll have 400.0 torr divided by P2 is equal to 11424,900. So 11,424,900. And then when I solve for P2, multiply P2 by both sides, divide both sides by 11 million, basically, and we get a P2 value equal to 3.5 times 10 to the negative 5 torr. Very, very small value. And this should make sense because we have a we're looking at vapor pressure at 100 degrees Celsius, which is very, very close to our melting point. So we are not very liquid, or we just reached a liquid point. So there's probably not going to be a lot of potassium vapor. Okay. Let's try this next question. A solution is prepared from 25 grams of benzene and 2.5 grams of an unknown compound. If we have a freezing point of 4.30, a normal benzene freezing point of 5.50, and a freezing point constant of 5.12 degrees Celsius over molality, we want to determine what our molar mass of our compound is. Okay, so when we set this up, this really doesn't need to be negative. It can be positive. It's just showing that it's a negative value. So we'll actually set this up to where our delta T is equal to delta T freezing is equal to 1.20 degrees Celsius by taking our 5.50 degrees Celsius minus 4.30 degrees Celsius, giving us 1.20 degrees Celsius as our delta TF. Then we'll put that into our equation. So remember, delta TF is equal to negative I KF molality. So we have our delta TF is equal to our I value of 1 times by 5.12 degrees Celsius over molality, canceling out that negative, times by our molality of unknown, right? We're going to be solving for this value. So when we solve for molality, we get a value of 0.234 moles per kilogram. Okay. We have our mass of benzene, so we're going to convert that into kilograms, 0.0250 kilograms. When we do that, that'll cancel out kilograms. That'll give us moles of 0.00586 moles. Then we could take our mass of our unknown divided by our moles of our unknown to get our molar mass. 2.50 grams divided by 0.00586 moles gives us 427 grams per mole. Okay. Next question, we're looking at the total heat that is required to convert 255 grams of frozen ethanol at negative 120 degrees Celsius to 80 degrees Celsius. Okay, so we have our melting point of frozen ethanol at negative 114 and our boiling point at 78.3. Heat of fusion 502 kilojoules per mole. Vaporization 38.6 kilojoules per mole. Our specific heat of our solid 0.97 joules per grams degrees Celsius. Liquid 2.57 joules per grams degrees Celsius, and gas 1.8 joules per grams degrees Celsius. Okay, so we're going to be using both grams and moles here. So the first thing I'm going to do is convert from grams of ethanol into moles of ethanol using my molar mass of ethanol, giving me 5.54 moles of ethanol. I can then do each of the steps. So we're starting out as a solid at negative 120 degrees Celsius, and we're going to go up to our melting point of negative 114.0 degrees Celsius. So here we have a temperature change, which is our final minus our initial. So it would be plus 120 because a minus minus a minus is a positive, giving us a delta T of 6 degrees Celsius. So our Q here is going to be equal to our mass, 255.0 grams, times by our specific heat of our solid, 0.97 joules over grams times by degrees Celsius, times by our delta T, 6.0 degrees Celsius. Multiply all this out, we get a value of 1,484.1 joules. I'm going to convert this into kilojoules. And it should have 2 sig figs. I'm converting into kilojoules because our delta H of fusion is in kilojoules. And our delta H of vaporization is in kilojoules. So instead of converting from joule or kilojoules to joules, I'll go the other way. Okay, now we're going to melt. After we get to that 114, we can melt. So Q is equal to our moles, 5.54 moles, times by our heat of fusion, 5.02 kilojoules per mole. Multiply that out, we get 27.8 kilojoules. Next, we're going to go from our melting point up to our boiling point. So the whole range of our liquid. So our delta T here is our final, 78.3 degrees Celsius minus our initial, which gives us plus 114.0 degrees Celsius, giving us a delta T of 192.3 degrees Celsius. Put that into our equation. Our mass times by our specific heat in the liquid phase. And then multiplied by our delta T, 192.3 degrees Celsius. Multiply all that out, we get a value of 126,024 joules, which I am going to convert into kilojoules, of 126 kilojoules. Here again, 3 sig figs. Next, we're going to evaporate. As we've gotten to our boiling point. So our Q will be equal to our moles times by our heat of vaporization, 38.6 kilojoules per mole, right here. Multiply that out, we get 214 kilojoules. Again, 3 sig figs here. And last, we're going to heat up from our 78.3 to our final temperature of 80 degrees. So our Q is equal to our mass, 255.0 grams, times by our specific heat in our gaseous phase, 1.80 joules per grams degrees Celsius, times by our delta T, which I forgot to do. Delta T is equal to 80.0 degrees Celsius minus 78.3 degrees Celsius, which is 1.7 degrees Celsius. That gives us a value of 780.3 joules, which would be equal to 0.78 kilojoules. And now that I've got each of my values, I can add all 5 values together to get my total heat. So 1.5 kilojoules plus 27.8 kilojoules plus 126 kilojoules plus 214 kilojoules plus 0.78 kilojoules. Put all that together, we get a Q total equal to 370 kilojoules. And with addition and subtraction rules, we have no decimal place here. And that'll be our answer. Last problem on here is filling out this table. This table gave a lot of people a lot of issues, so I'm going to show you guys how to go through this table and answer this, as this will absolutely be on the test. So this table kind of has 2 parts. The top part is our different concentrations. The bottom part is kind of a way to solve the information. It's kind of there to guide you through this information. So we are starting out with percent by mass and density for the first one, and then molarity and density for the second one. So we can start out with both of them by assuming 1 liter, which is what I've kind of told you to do down here, right? Ask for the moles of solute in 1 liter, grams, solvent, and grams in 1 liter. So we're going to assume 1 liter. When we assume 1 liter, that's the same thing as 1,000 milliliters. So we can multiply our densities by 1,000 milliliters. That'll give us our mass of our solution. Okay, and I'm actually going to do it for both of them. Okay, and then once we have our massive solution, we're going to start and manipulate our concentrations. So here we have 5%. 5% of our solution is going to be solute by mass, and then the other 95% of our solution mass will be our solvent. So we can just take our mass of our solution, multiply it by 0.0500, our fractional percentage, and that will give us our mass of our solute. Okay. And then we could either take that value, subtract it from 1018, or we can multiply 1018 by 0.95. And that will give us our grams of solvent. Okay? And our solvent in this case is water. Now that I've got my grams of each of my substances, I can go into moles of each of my substances. So I'll take 50.9 grams of my C12H22O11, use my molar mass of 342.2965 to get into moles. 0.148 moles of C12H22O11. Same thing with my water, so I could take my 967 grams of water, use my molar mass of water to convert into moles of water. Okay. And now that I have these pieces of information, I can solve for all of the rest of it. So molar concentration is our moles of C12H22O11 divided by liters of solution. Okay. Our moles are 0.148. Our liters is 1. So that gives us 0.148 molar. Next we have moles of C12H22O11 divided by kilograms of water. Okay, so 0.148 moles divided by our kilograms of water. So it's 0.967 kilograms, so taking that 967 divided by 1,000. And we get a value of 0.154 mole. Make sure all of these are boxed off. Your answer should always be boxed off, so I can very easily find them. Okay? Now the last thing we need is our solute mole fraction, so that's our moles of solute. Divided by total moles, which is 0.148 moles divided by 0.148 moles plus 53.7 moles. Divide that out. We get a value of 2.75 times 10 to the negative 3. Okay. Now, we're going to follow the same basic process here. Okay, for our sodium sulfate, or sorry, not sodium sulfate, ammonium sulfate. We don't have a mass percentage, so instead we're going to start with our molarity. So we have a grams of solution. We can also get our moles of solute by multiplying by 1 liter. Okay, next, let me do that all over here. So we could take our 0.885 molar times by 1 liter. That gives us 0.885 moles of ammonium sulfate. Okay. Then we can convert that into grams using our molar mass. And we get 117 grams of ammonium sulfate. Okay. Now, we have our mass of our solution up here, and we have our mass of our solute, so we can get our mass of our solvent. 1060 grams minus 117 grams gives us 943 grams of water. And then from that 943, we can convert into moles using the molar mass of water. Giving us 52.4 moles of water. And now again, we have everything we need to solve our different concentrations. So our first one is mole concentration. So this is going to be moles of ammonium sulfate divided by kilograms of water. So moles of ammonium sulfate, 0.885 divided by our kilograms of water, 0.943, giving us a value of 0.938 mole. Now, as we notice, hopefully, our molality will almost always, especially for dealing with water, be larger than our molarity. Okay. Next is our mass percent. So we need grams of ammonium sulfate divided by grams of solution. Okay. So we're going to take our 117 grams of ammonium sulfate divided by our total grams, 1060 grams, multiplied by 100, giving us a value of 11.0%. And lastly, we're going to have our solute mole fraction. So moles of ammonium sulfate divided by total moles. So 0.885 moles divided by 0.938 885 plus 53.7. That will give us a value of 1.66 times 10 to the negative 2. Okay? And that's everything. Hope you guys understood that, but please come see me if there's something you still don't understand. Bye, y'all.